our next application of integrals involves finding the center of gravity, or also referred to as the center of mass, or sometimes called the centroid of an object. And that's a useful thing because we use that many times when we have the force of an object or something like that. We center around this idea of it coming from that center of mass or acting at that center of mass. And so it's a great way to simplify things once we know how to do that. So let's talk about what the center of mass kind of looks like. If my object were just a square or even a rectangle, it would be pretty easy to find, right? It would just be, I'd go halfway down the length, halfway down the width, and it would be right here in the middle. You know, it's kind of the central base of this area. Pretty easy to figure out. Same sort of thing if I had a circle. Again, if I had a circle, and that's not a perfectly drawn circle, but pretend for this purpose, the center of mass would be right at the center of the circle. What if I had a triangle? Well, if I had a triangle, one way to think about that is it's basically half of a rectangle. So instead of being halfway down this length, I would need to be a quarter of the way down this length. And instead of being halfway up the height, I'd need to be a quarter of the way up the height. So the center of mass there, and it would have been smarter if I drew this to scale, it would be somewhere here where it's a quarter here and a quarter of that one. So somewhere about right there. Well, that's 1/4 of the length. So it's still not too hard to figure it out if I've got an easy shape like that. But what if I have just a more random shape? And there we see a truck, maybe. Not a well-drawn truck, more like a kindergarten truck. But yeah, where would the center of mass be? Would it be here? Would it be here? It's tough to tell. Maybe there? It's probably not dead center. There seems to be more mass this direction. Maybe more towards the bottom. I don't know. We'd have to figure that out. It's a little bit tougher to do. So what if we applied that to functions? What if I had a function drawn? So let's say I have a random function that looks something like that. So where I would find the centroid would be, again, somewhere, it's wherever the average length and kind of average height of this is. So somewhere maybe in here. Again, I'm just kind of guessing at it. But I know it's going to have some sort of coordinate x and y. Okay, well, one of the first things I need to do to figure out where the centroid is think about what is the entire area of the curve I have here. And so how do I find area? Well, we've done that several times, right? That the area under the curve, or the area under the curve, which is the shape I'm looking at right now, is the integral of y dx. And where I would end that would be dependent on where it crosses the axis and that sort of thing. I would have to determine that part. So then what we have for our centroid is the following. That the x component is the integration of x times y dx divided by the integration of y dx, which is the area. And this is also called the first moment of inertia. So I could use that to get the x-coordinate of the centroid. For the y-coordinate of the centroid, I'd have a similar formula where it is 1/2 the integral of y squared dx on top, and the bottom is still that same function that represents the area. So basically what we're doing is integrating a function over an area and dividing it by the area of this thing. This is similar to when we wanted to find an average value of a function. We took the area and just divided it by the distance or the x values which we were looking across. Same sort of thing, only now we're going one dimension higher. So we're integrating essentially x times y over and dividing that over the area. Another thing to look at that is like, well, what if I turn the axis and looked at it the other way? Well, if I turn the axis and look at it the other way, this would be an equivalent equation. So another way I could look at this is in terms of the derivative with respect to y. And so if I just kind of flip the equation around, sorry, that would be dy. I use this function to find it with respect to x. If I just kind of flip things sideways, I would still have, if I multiplied x times y and integrated with respect to y and divided it by y integrated with respect to y, it would give me the same thing mathematically. So this is really just doing these two things, only since my function I'm going to get my function in terms of x, it makes more sense to translate it this way rather than I would have to find the inverse function and do all sorts of things. And also you run into things like this is the inverse of this is not a function because it has multiple values across the same way. So you can run into problems like that. So those are the basic rules for center of gravity. Mainly we need to know these two. We need to remember the area equation. We need to remember that's how we get the x component, and that's how we get the y component. So let's look at an example. So say we're given this function, y of x is negative h over b times x plus h on the interval 0 to b. Well, let's think about what that looks like real quick. So we'll sketch it out. So there's our graph. What do we know about this? Well, we know if we put in 0 for x, it starts here at h. We know it's linear with a negative slope, so it's going to look something like this. And we know we need to go from 0 to b. So what does it look like at b? Not surprisingly, if we put in b, we get negative h over b times b plus h, so we get negative h plus h. We ends up that's where it crosses 0. So this point is b. So essentially what we're looking at is our triangle with the width of b and the height of h. So already from what we talked about before, we can expect for this to be somewhere around here, around the 1/4 and 1/4 mark. But we want to show that by going through the calculus of everything that we get to the same answer. So let's start by, we know that area is in the denominator, so we're going to calculate that first. And again, we know that area, which is going to be our denominator, is the integral of y dx. So then we can just plug in our function and evaluate the integral we want to find. So we're integrating from 0 to b, because that's our interval, negative h over bx plus h. Just our y function gets put in there. And now we can get the antiderivative. So when we do the antiderivative, raise the power divided by the new power, so we get x squared and the 2 on bottom. Raise this to x to the first, divide by 1, so it just becomes hx. And again, we don't have to worry about the plus c because we're doing a definite interval. And then we plug in our values. So we plug in b and get that, which we'll simplify in a second. When we subtract, there's x in every term at 0, so this half goes to 0, so we don't have to worry about that. So let's just simplify. Okay, so when I simplify that, I get the b squared, one of those cancels out, so I get negative hb over 2. On this side, I just got hb. I can add those together and get a positive hb over 2. And so, again, that's just the area of it, which makes sense. We know area of a triangle is 1/2 base times height. That's 1/2 base times height. So pretty obvious, again, because we know the geometry of it, but the calculus is confirming what we expected. All right, but remember, area is not what we were actually looking for in this. We're trying to find the center of gravity, and our equation to find the x value of the centroid is to take the integral of x times y, integrated with respect to x, and divide it by that area. So let's calculate what the numerator of this is. So to get the numerator, remember x times y dx. For our particular example, we're going from 0 to b, x. Our y function is negative h over b times x plus h, and we're going to integrate that with respect to x. So first we want to simplify that a little bit. So we distribute the x, and we end up with this. The integration from 0 to b of negative h over b x squared plus h times x dx. Okay, so we transferred everything over to another page because we ran out of room on the previous one. So again, we're just trying to find the x bar numerator, and we know it's this function. Now we need to actually get the antiderivative. Again, it's just a polynomial with a little bit of strange coefficients. So x squared, raise the power to 3, divide by the new power. X, raise the power to squared, divide by the new power, and we're there. Now we plug in the values. Again, we're fortunate because not hard to plug in b. We'll be able to simplify that in a minute. And when we plug in 0, again we get 0 over here to the right. So we can simplify that expression as we just said. So when we simplify that, this first term, we cancel out a b, so we get negative hb squared over 3. The second term is just hb squared over 2. So if we kind of separate that out for a second, we get hb squared, negative a third on this first one, plus a half from the second one. And when we do that addition, we get 1/6. So it ends up that our numerator is hb squared over 6. Then we have to remember that's not the answer we're actually looking for. That's just a part of it. What we're actually remembering trying to find is x bar, which is the x bar numerator we just calculated, divided by our area. And so x bar is actually equal to our area, which our numerator, which is hb squared divided by 6 over our area, which is hb divided by 2. And so essentially what this turns out to be is hb squared over 6 times 2 over hb. And it's easy to see from there, the h is canceled, one of the b's cancel, these will cancel and leave me at 3. So it actually ends up being our base divided by 3. So my geometry was wrong earlier. We get that it's the base divided by 3 for the x bar component. All right, but even with all that, we're still only halfway through because we also need to find y bar, the y coordinate of the centroid. And remember again, the y centroid formula was 1/2 times the integral of y squared dx divided by the integral of y dx, which was again area. But we haven't solved that part yet. So y bar, the numerator, is 1/2 the integral of y squared dx. We can substitute in our actual formula here. So we have 1/2. We're going from 0 to b is our limits. There's our function, but we have to square it. So we have to do a little extra algebra here up front, a lot more complicated than just doing x. We'll have to actually use FOIL or whichever method to square the function. So remember, when we square a function of a binomial, we get the first term squared. So make sure we square everything. The h squared, the b squared, the x gets squared. That's the first term. The last term is just the last term squared, so it's just h squared. And then the middle term is 2 times the product of the two terms. So this is negative h over bx times h. So negative h times h is h squared times b, or b within the denominator, and we still carry along the x, and we have 2 of those. So wording got confusing, but that's the number there. Sorry about that. All right, now we want to integrate it, do the antiderivative. And again, before simplifying, again, polynomials, easy to deal with. Raise the power, divide by the new power. Raise the power, divide by the new power. Raise the power to 1, divide by 1. Okay, so we have all that. Now we have to solve, we have to plug in our values at each point. The difficult part here being, remember to keep 1/2 is going to get multiplied by everything through here because it was outside of things. So that's why I'm keeping my brackets right. So I just plugged in b cubed for these, did a little bit of simplification. I'm 3 up front there. These 2's canceled out, so I really just have h squared over b, and then that becomes b squared. And then that's h times b. Again, plugging in 0 gets me 0, which is really nice. So now we can simplify this side. We simplify things. B squared cancels out, we just get a b there, so h squared times b over 3. One of these cancel out, so we just get an h squared times b. That's still h squared times b. Nice thing here, we have a negative value and a positive of the same thing. Those will cancel out. So we really just have this term times the half, and so we'll end up with 1/6 sixth h squared times b. And again, remember that's just y bar of the numerator. So we haven't found our answer yet. We have to divide it by the area to get what the actual centroid is. So y bar is our y numerator divided by the area. We plug in those values. h squared b over 6 divided by hb over 2. We get that, this is the same as just flipping this over here. Multiply those things together. We can see lots of things cancel. The b's cancel. One of them cancels. We're left with an h here. 2 and 6. The 2 cancels and leaves the 3 there. So we're left with h over 3. So actually our final answer is that the centroid, which is x bar, y bar, is b over 3 and h over 3. So it turns out the centroid of our triangle is 1/3 the way across the base and 1/3 the way up the height. Again, we could do this for much more complex formulas. As long as we had the formula, we could do it for complex things like this. But we've shown that this will work on something we're familiar with. And these are the key equations that we need to know for that. Is that for center of gravity or center of mass or centroid, if it asks for any of those three things, we need that x bar is the integral of xy dx divided by the integral of y dx. And remember that this integral of y dx is just the area. And for the y bar, it's 1/2 y squared, 1/2 the integral of y squared dx on top. And again, it's the same function for area on the bottom.